Okay, so again we're going to solve the heat equation, but this time the boundary is not 0. Okay, so let's go back to what we were talking about before. The one-dimensional heat equation is like a one-dimensional rod where there's insulation surrounding it. And then the left part is touching ice so that it's kept at 0 degrees Celsius. And let's say the right side is exposed to a room that's 20 degrees Celsius. Okay. And let's say initially the rod here was cold. It's 0 everywhere. Okay. But then because the right side is kept at 20, this right side will start rising, right? And then at some point it's going to rise up to 20. Well, it says it's always 20, so let's say it's kept at 20, but I guess after some time the graph of the temperature, the uxt at time t will be something like that, right? Where this side will be 0, this will be 20. Okay, and then eventually it will
be a straight line.
It will be a straight line, right? Eventually at time t infinity it will be a straight line. Yeah. So now let's try to solve this. Because we just proved the the uniqueness of the solutions, we can with more confidence not try to solve this, but just come up with a solution. We're just trying to make guesses, good guesses, that would satisfy all the conditions that's given to us. And if it satisfies, that's it. That's the solution because of uniqueness. Okay? So let's try that. And here, really the idea is that at time t infinity, it's going to be this straight line. Okay? So let's see, 0 to 4, and straight line 0 to 20. What's the slope? Change of y is 20, change of x is 4, so slope will be 5, right? So we know that ux infinity should be 5x. So that's our physical intuition of what's going to happen. So what we do is we try, again, like the idea before, we don't try to satisfy everything at once. Just try to find something that satisfies some conditions and see what happens after that. So what we do is we just start with uxt that looks like 5x 5x, right? Plus some function of t. Let's just say some function of t. Okay? No, actually, it's not even that. We just say, that technique is for later. Okay, so when the right side is a function of t, we're going to do that. So for this one, it's easier. We just say uxt is 5x plus v xt. And then look at what v satisfies. Okay? So if you do ut, what do you get? If you differentiate 5x by t, you get 0. And therefore, you just differentiate v by t, and that's it. Okay, ut is 0.3 uxx. right? So this is going to be same as 0.3 uxx. Oh, so let's try to figure out uxx first. If you differentiate u by x, what do you get? You get 5 plus vx, right? Now differentiate one more time, what do you get? You get
Vxx.
You get vxx because 5 differentiates to 0, right? So because ut is same as uxx times 0.3, if you multiply 0.3 both sides, then you see that this is equal to this, which is equal to this, is equal to that. All good? In other words, even if there was a 5x there, v still satisfies the heat equation. Do you agree? Okay, v still satisfies the heat equation. And so that's the first thing. Vt would be 0.3 uxx. And now let's look at u of 0t. Well, that's 5 times 0 plus v of 0t. And because u of 0t is 0, we get v of 0t must equal to 0. Okay. Same thing here. Maybe it's better to say that v is u minus 5x, right? So because v is u minus 5x, that means v of 4t is u of 4t minus 5 times 4. What's that? What's u of 4t?
20.
20, right? So it's 20 minus 20, which is 0. Right? Okay, so that's better. That what happened was now you have v to be the solution of the heat equation with 0 boundary conditions in both endpoints, which is exactly the questions that we solved before. Right? That's nice, right? Okay, and then furthermore, oh, I guess this is something different. What's v of x0? This is u of x0 minus 5x. But what is u of x0? 0. So you get 0 minus 5x, which is negative 5x. Okay. So now we have, what we did was we converted the question that we had originally into a new differential equation with 0 boundary conditions, and the trade-off is that the initial condition is now no longer 0, it's negative 5x. We just have to solve this one, which we do know how to solve, right? Okay? Now, since you guys have the exam tomorrow, this will be a good review for the exam tomorrow, because definitely you might not be given when it's non-zero at the endpoints. That's for the next exam, but definitely for tomorrow you're going to have something that's 0 at both boundaries. Okay? So let's try this one. So we apply separation of variables. What is separation of variables? You say vxt is a function of x times function of t, and you're looking for all the functions that satisfy the initial heat equation and the boundary conditions. But you don't allow it to set, you don't want the initial condition yet. Okay, so you only apply this much. Okay. And if you plug it into the heat equation, if you plug into the left side, what do you get? If v is x times t, what is vt?
Xt prime.
Yeah. X of x, t prime of t. Okay, what is uxx? That's differentiating, where do you put u? Vxx. What is vxx? That's like taking this and differentiating twice in x, right? So it'll be x double prime of x, t of t, with 0.3 in the front. Okay, so that's what you get if you just take this and plug in the heat equation. Okay. In addition to the, and then once you have this, what's the trick?
Divided by 0.3x.
Yeah, you divide both sides by kxt, right? So you divide both sides by k, which is 0.3, x of x, t of t. So that when properly things are canceled, you end up with t prime of t over t of t, 0.3t, equals to x double prime of x over x of x. And the only way you can have a function of t equals to a function of x is if they're both equal to a constant. Okay, it's a constant. So we say it's equal to a constant, but for ease of future calculations, we're going to name that constant as negative lambda. You can just say it's equal to c. You can still proceed the calculation. It's just a bit more confusing if you do it that way. So just remembering to divide by kxt and then setting the resulting constant as negative lambda is helpful. Okay? So just remember those two. Let's continue after this. Okay, now the boundary conditions are given. So we have v of 0t equals to 0, but that means because v of 0t means x of 0 times t of t, that has to equal to 0. Now, this either means x of 0 is 0 or t of t is 0, but we don't allow this one. Why?
Because it's trivial.
Because then v of xt will be a trivial solution. We're looking for all possible non-trivial building blocks to also match the initial condition, right? So that defeats the purpose. If we get v as 0, we already knew that that's a solution satisfying the first one and the second condition, the boundary condition. So that doesn't help us anyway, so we only look for x of 0 equals to 0. In the same way, if v of 4t equals to 0, that's going to say x of 4 times t of t equals to 0, and that's going to give you x of 4 equals to 0, or t of t equals to 0. Again, we don't allow that because that's going to give us trivial. So now here's what we have. We have x of 0 is equal to 0 and x of 4 equals to 0, along with this condition here. If I multiply x to the other side and bring it this side, I have x double prime plus lambda x equals to 0 with x of 0 and x of 4 set to be 0. So this is what's called the Sturm-Liouville problem, because it turns out that in general, for most values of lambda, this never gives you a non-trivial solution. But we were looking for non-trivial solutions, right? So if you put that condition that x cannot be all 0, then you do have solutions that satisfy both of them, but for only specific lambda values, right? Now, I think either in the practice exam or the homework, you've done this question with 4, I think. If not, let me know, then I'll do it. But this, I don't want to spend too much time doing this, but it turns out that the lambda values are n squared pi squared over 4 squared, which is 16, for n equals to 1, 2, 3. So in other words, lambda cannot be 0, lambda cannot be negative. The only values that give you non-trivial solutions are when lambda is these numbers for n equals 1, 2, 3, and infinity. And for that value, it turns out that x would be some multiple of the following function, sine of n pi over 4x. And do check that if you plug in 4 in here, what is that? You get sine of n pi. What's sine of n pi? 0. So and that's a very good way to check if you did it correctly. So if you, after doing all the work, try plugging in the endpoints and do check that x does become 0 at those endpoints. Okay? So we have that, and then now we replace the lambda n squared pi squared over 16 back into this equation, which gives you the following. We get, well, I'll have to erase this. We get that t prime is equal to negative 0.3 times n squared pi squared over 16 t. And I told you that this equation is very similar to like y prime equals to ky. How do you solve this?
Exponential.
Yeah, I mean, you can easily see that the solution is e to the kt, right? Because if you differentiate this, k comes down, so it just matches, right? So you can just go straight to the answer this way. T of t equals to e to the negative 0.3 n squared pi squared t divided by 16. Because this over 16 is this k. Or if you're not satisfied with just looking to see if it holds or not, you can actually show that these are like some constants times this is the only solution, because if you divide both sides by y and you integrate, then y prime over y is ln of y, right? So you have, that gives you ln of y equals to k x plus c, and then you take e both sides, then y is indeed e to the kx. So that's like the quick way to do it using something called separable differential equations. But it should be obvious, right? So this is what you get. And then, because we had v equals to x times t, and we found both x and t, it's this one times that, right? So we can say that in general, it's some constant times e to the negative 0.3 n squared pi squared t over 16 sine n pi over 4x. Okay?
T prime.
Did I make something? Make a mistake? What?
How do you get T prime? Where it's from?
T, you mean this one?
No.
This one comes from here. This equals to this. You multiply this to the other side, and you get this. All right, so what does this achieve? Well, here's what we achieved. This function here will satisfy the heat equation, Vt equals to 0.3 Vxx, and also the two endpoints, V0t and V of 4t equals to 0. Okay. But not only that, you can take, see, this is not just a single solution, this is infinitely many solutions, because n can be 1, 2, 3, and so on, right? So there are infinitely many solutions, and you can take any of those two and add them up. It will still satisfy this, it will still satisfy that. Because if you add two things, differentiation is linear, so it will still satisfy this. Right? And because the boundary conditions are 0, adding two zeros is still 0, right? So any two of them added will satisfy both. But what stops you from adding 3 or 4 or all of them, right? So what you do is you take the maximum possible, just add every solution that you found. So what you can do is we can replace, so C could be different for each n value. So C1 could be different from C2 and C3. So replace C by Cn. And you add them up from 1 through infinity, and then you call that as your V. That's still going to satisfy the heat equation and the two boundary conditions. We still have one more condition to satisfy. What is that? The
Vx0?
Vx0, which is the initial condition, right? So Vx0, we wanted negative 5x, right? Okay. What should it equal to? You plug in t equals to 0. If you plug in t equals 0, e to the 0th power is what? 1. So if I plug in t equals to 0, this thing turns into n from 1 through infinity of Cn times sine n pi over 4x. So to figure out what Cn satisfied negative 5x equals to the sum of sines, we have to use what? We have to use the sine series. So let's compute the sine series.
Professor?
Yes?
I feel like this question comes to why can't we use cosine series?
You can't use cosine series. You're forced upon the sine series by what's
right.
the building blocks that we have. So it has to be a sine series. Can't be the cosine series. And it turns out that for Neumann boundary conditions, you will get cosine. For the Dirichlet is when the values are fixed at 0. In that case, you get sine. Neumann is when v differentiated by x is equal to 0, where the endpoints are insulated. Then you're going to get cosine. And remembering that helps you to do the calculation with more confidence, right? So as long as the values at the end are 0 and you got sine, that's good. Okay? If this said Vx, this should have been cosine. Good? Right. So now let's write down the formula for Bn. Bn is 2 over L, 0 to L, f of x times sine n pi over L x dx. And that's exactly the Cn's that we're looking for. So our Cn for that case would be 2 divided by 4, 0 to 4. F of x is negative 5x times sine n pi over 4 x dx. And we can do this calculation by using tabular integration. Or maybe I can just do regular antiderivatives. Okay, so you can do this by using, what's that? Integration by parts. So integrate the sine. Negative sine integrates to positive cosine. Okay, with n pi over 4 x. So 5x. So 5x still is there. But then because of the integration, 4 over n pi will be appearing in the front. And you plug in 4 and 0. Minus whatever you did not integrate in the next stage, it gets differentiated, right? So you get 2 over n pi. This has become 2 over n pi. Integrate 5 times cosine n pi over 4x dx. Integrate from 0 to 4. And it turns out that this part becomes 0. So I'll skip some calculations. Cosine, because you're integrating a cosine function over its full period, this will give you 0. Or another way to see it is cosine integrates to sine. When you plug in 4 and 0 into sine n pi over 4x, it will create 0. Okay, so this part will give you 0. When you plug in 4, half of 4 is 2. 2 times 4 would be 8. 8 times 5 would be 40. So you're going to get 40 n pi, negative 1 to the nth power. All right, and then when you plug in 0, because you're plugging in 0 into 5x, you get 0. So this is the only thing that you get out of this integral. And because now you've figured out your 40 over n pi, your Cn to be 40 over n pi times negative 1 to the nth power, now we have the solution for V. So the conclusion is that Vxt is equal to summation of n equals to 1 through infinity of 40 over n pi, negative 1 to the nth power, e to the negative 0.3 n squared pi squared over 16t times sine n pi over 4x. Is that the answer?
No, because we have to get the u.
Yeah. So the question was so long that the solution was so long you forgot what the question was. We weren't looking for V. We were looking for uxt. What is uxt? Is 5x plus this thing. Right? So the real answer is 5x plus summation n equals to 1 through infinity of 40 over n pi of negative 1 to the nth power e negative 0.3 n squared pi squared over 16t sine n pi over 4. Okay?
Firstly, I thought we will prove that V is 0.
No. V cannot be 0. Of course not. V equal to 0 wouldn't satisfy the initial condition, which was equals to negative 5x. There's no way. Yeah. Okay, so that's the answer. Now, we do like this solution because what happens if you send t to infinity?
5x.
Because you have e to the negative infinity, e to the negative infinity is 0, right? So this humongous sum will converge to 0 as you send t to infinity, and you do get 5x, which agrees with our intuition that the temperature distribution at infinite time will be a straight line. So not only it's a solution, it does agree with our physical intuition, which is nice. Okay?
So we definitely have to use 5x as the...
Yeah. So see, the reason we decided to call uxt as 5x plus vxt was from that intuition. It must be something that would die away as 0. So you're wrong in saying that v is 0, but it is true that when you send t to infinity, v goes to 0. Yes?
Did we prove that the physical intuition of being it becoming 5x is being on a straight line?
So let's see. I guess the question is, if the endpoints are fixed as some temperature, should it always be a straight line at time infinity?
Right. Considering the
So it's like this. To answer that question, you look at the heat equation. Actually, let's go back to U. See, at some point, if you allow infinite time, if the boundary values are fixed, then you would expect the temperature distribution not to change much, right?
Right.
Yeah. Which means the partial derivative with respect to t would be 0.
Right.
Yeah. So at time t infinity, ut would be 0.
Correct.
Right? Now what does that mean? That means that 0 is equal to kuxx, which means second derivative is 0. What kind of function has second derivative 0? Well, if you integrate both sides, you get a constant. You integrate again, so it's a straight line. Okay. So the heat equation actually shows you that if the system stabilizes its temperature distribution in some shape, then it has to be a 1.